We're back with another related rate example. I wanted to go over a problem like this with you because this is a very common type of problem. We call it a conical tank problem. And we see lots of variations on this problem. So in this particular one, there's water pouring into a tank that's shaped like a cone. We see problems where they vary the fluid that's going in. Sometimes instead of water pouring in, there's water pouring out. Sometimes, my favorite, they call them in and out problems. There's water both pouring in and pouring out. But we see this problem a lot. And the first thing everybody always says to me is, really? A tank shaped like a cone? Why couldn't the tank just be a cylinder? And my answer is, if it was a cylinder, we wouldn't need calculus. Okay. So you're going to see oddly shaped things. But I would like to say that I Googled conical tank. And other than a bunch of calculus stuff coming up, there are tanks, and actually these are really common. I didn't find any tanks that were fully conical, to be fair. But there are a lot like this that are cylindrical and then they go to a cone on the bottom. And I assume that that is to get the maximum amount out. This appears to be where the drain is right here. So if we're thinking about something pouring out of here, you can imagine, again, since this is cylindrical, if something is pouring out of here, the level in this tank is going to drop, and it's going to be a pretty constant drop. But once it turns into the cone area, the rate at which that level's dropping is going to change. And that's where the calculus comes in. I don't need calculus for this part of the tank. The sides of the wall are the same, so if I start draining it at 1 liter per minute, the water level is going to drop steadily. I don't need calculus for that. That's algebra, right? It's when that rate starts varying that we need calculus. When you get down into that cone part, that's where the rate starts varying. Okay. Now, if you're wondering why that is, that goes to the other picture I have here. I like to think that this is an olive oil bottle. I don't know if I'm the only person in the world who does this, but if you go down to the Strip District to get your olive oil in Penn Mac, they have these big, giant barrels of olive oil. They are not conically shaped barrels. They are just regular barrels. And you get your bottle, looks a lot like that, doesn't have a handle, and you fill it up your darn self, right? I spill olive oil all over the floor almost every time. Almost every time. Because what happens is, I start filling and I'm standing there, right? And I watch the oil come up, and it's rising at a pretty steady rate, right? And then right around here, something changes, right? It was rising at a steady rate because it takes a certain amount of olive oil to fill, kind of create a layer in this bottom part, in the cylindrical part. When you get up here into the neck of this bottle, it takes a lot less olive oil to fill a layer. So whereas maybe an ounce of olive oil down here might only be a very thin, like a very small depth, up here you put that same ounce of olive oil, guess what? It's going to be a lot deeper to fill up because this is so narrow up here. Now in this case, it would be rising at a steady rate down here, be rising at a steady rate down here, and then right in here, you see where this funky part is, where it angles in? At that point, that level of olive oil is going to be rising at a different rate. Now we know it's going to be increasing because, man, the bottle is narrowing, right? So the rate at which this level is rising very quickly increases. And then I don't pay attention because I was counting on the level that it was rising before. And then before you know it, I go, oh my gosh, it's about to overflow. And before I can turn the valve, there's olive oil on the floor. Okay, so the idea of this is that depending on the shape of the container, the rate at which a level of fluid or whatever it is rising is going to vary. If your container has a constant shape, or like a constant cross section, if you will, that the rate at which the level is changing is going to be the same. It'll be a constant. It's when the shape isn't shaped, it's when the sides aren't like this, it's when that starts varying, when the cross section starts varying, that the rate at which the object fills changes. So when we get something like a conical tank, My rate is constantly changing. The rate at which the water level is rising or falling is constantly changing. So we see these problems a lot, and there's one, I don't want to say a trick, but maybe something that you wouldn't have thought of, and once you can kind of get over that part, these problems are pretty easy. They're not nearly as hard as they seem. Okay, so let's do it. Okay, the first thing we know, well, let's read the question, right? Okay, so it says water runs into a conical tank at a rate of 9 cubic feet per minute. So those units are pretty interesting, right? Cubic feet per minute. Hopefully you recognize those units. Anything cubic is going to be a volume, right? So they're giving us a rate of volume. They're telling us how much water is pouring into the tank, the rate at which water is pouring into the tank. Again, it's a volume per minute. So 9 cubic feet per minute. The tank stands point down, as you can see, and has a height of 10 feet and a base radius of 5 feet. Now, I always think it's interesting that they call that the base radius, because I think of a base as on the bottom, but when you're talking about a pyramid, regardless of its orientation, the base is the circle part. Okay. Yes, I am. Thank you. All right. Okay. So we want to know how fast the water level is rising. Now, if you think about this, when you start pouring water into this tank, this bottom part, this point, is going to fill up really fast, right? Because there's not a whole lot of space down there. So you pour 9 cubic feet per minute, you start pouring in, you pour 9 cubic feet, it's going to fill up this bottom pretty quickly. The more water is in the tank, though, as you can see, once you get to the top, if you want to fill an inch up here, you're going to need a lot more water than if you want to fill an inch down here, right? So this water that's pouring in at a constant rate is going to cause the water level to rise, but the water level isn't going to rise at a constant rate. And that's their question. How fast is the water level rising? Okay. Since it's not at a constant rate, they have to give you the instant that they want to know it. And they want to know how fast the water level is rising in the moment that it is 6 feet exactly. Okay, so if we label up our diagram, the radius of this tank is 5. The radius that they're, the height of the water, they gave us a radius, they gave us a height. The height of the water they're interested in is 6 feet, right? So I've got a total of 10 feet that I can fill. They want to know what's going on at exactly 6 feet. Now, notice the radius of the tank is 5 feet, but at this moment, the radius of the water itself isn't 5 feet. It's something smaller than that, right? At the very bottom, the radius is 0. The radius of the water, the cone that is the water, is going to slowly get bigger until it gets to 5 at the very tippy top. But it's not 5 anywhere other than at the top. The radius of this, if you look at a cross section, is smaller. So this is a radius, but I don't know what it is right now. Okay. So I've got water pouring in. So dV dt, right? They're not giving me a total volume. They're giving me the rate at which the volume is changing. They're giving me a dV dt. Now, notice I made it positive. It is a positive 9 cubic feet per minute because the water is pouring in. If what they said was we were draining water at 9 cubic feet per minute, we'd put a negative on there. And then what we would expect for the rate at which the water level is changing would be a negative as well, because the water level would not be increasing, it would be falling. If water's pouring in, the water level is going to come up. If water's pouring out, the water level is going to come down. So down is going to be a negative rate of change. All right, so I have V coming in at 9.3, and they want to know how fast the water level is rising. So I need to give the water level a variable, right? I'm going to call it Y just for fun, right? And the question is, what's dy dt? So I need an equation that relates the stuff they gave me, in other words, the volume, to the thing I need to know, which is this Y value, the water level. So I need an equation that links volume to Y. and y being the height of this cone. Does anybody remember the equation for the volume of a cone? I am obsessed with this equation. The volume of a cone is exactly 1/3 of the volume of a cylinder. In other words, if you have 3 cones that are the same height and radius, and you have a cylinder with that same height and radius, you can shove all 3 of those cones into that cylinder. I find that fascinating. So, volume of a cylinder is pi r squared h. So a cone is going to be 1/3 that. So 1/3 pi r squared h. All right, now, it says use implicit to turn it into a rate equation. All right, so I have V equals pi over 3 r squared h, and this is where I want you to make sure you're being careful when it comes to these problems. Before you take a derivative, make sure you have everything you need. And by that I mean not only do you need an r and an h, but make sure you have those rates. All right, so let's take a look at this. When I take the derivative of this, I'm going to get a dv dt. Good, they gave me dv dt, and it's pretty important to the problem. I'm going to get a dr dt, which is a bit of a problem. I don't have the rate at which the radius is changing. I don't know anything about the radius. All I know is that it's not 5 and that it's growing as I go up. Okay, so that's a problem that I'm going to need to fix. Okay. The height in this case is what we called y. And when I take my derivative, I'm going to get a dy dt, which is again a good thing because that's what I'm after. The problem is this. I don't know the radius of that cone of water. And I also don't know at what rate it's changing. So that's a doubly bad problem. Right? Because of that, I got to get that r out of there. Before you take the derivative, you've got to get any variable that you don't know about out. If you don't know the rate at which r is changing, you can't solve this equation with an r in it. Okay? If we didn't know the rate at which h was changing, or y, whatever we're calling it, we wouldn't be able to solve this if we didn't have the dy dt or the dh dt. So if you have a variable in your equation, but you don't have any information about it, you got to get it out. So we've got to get that r out of the equation. It's sort of like a system of equations, right? I have an equation here that has too many variables. So what I need to do is find some other relationship that I can use, some other true statement that I can write about this situation that I can use to do a substitution and eliminate that r, get that r out of my equation. In other words, I need to find a way to rewrite r either in terms of v, because I have a dv dt, or in terms of h, or in this case we called it y, because I have a dy dt. Okay. And that's where this trick comes in. I'm going to show you this. This is true of every conical tank problem. Okay. When we're picturing in 3D, sometimes it's difficult for us to picture, again, like cross sections are in 2D space, and sometimes we don't even think of it. But here's what you need to know. This cone of water, geometrically, is always, no matter what the water level is, going to be similar geometrically to the big cone of water. In other words, the ratio radius to height has to be the same, whether your cone is little or in the middle or almost all the way to the top. It's always going to be true because it's a cone, the nature of a cone, right? That the radius and the height are going to have the same proportion. That proportion is going to stay constant. Okay, so look what I know. If I write a proportion of radius of the tank to height of the tank, that's going to match the radius of the cone to the height of the cone. Well, the radius of the whole tank is 5, and the height of the whole tank is 10. For my cone of water, I do not know the radius, but I know that my height is 6. Oh, where's my pen? Okay. So this is going to do two things for me. Okay. It's going to help me get this r out of the equation, because now here's what I know. My monkey. Okay. The radius to height ratio in this case is 1/2. If you hate fractions, you could write that ratio the other way and get it too. So that helps me. Look what I know. The radius of this tank at any point is half of the height. So right now, I can go over here and replace this radius with a 1/2 h. I know that has to be true because the radius to height ratio of the tank is 0.5 or 1/2. Then the radius to height ratio of any of the water at any point is 0.5. That's the kind of leap you have to make in these problems. If you don't make that leap, if you don't realize, hey, I don't have a dRdt, there's a problem here, and take the derivative, you're going to have an equation that has an r and a dRdt in it, and you're not going to be able to get them out. So you have to make sure every single time you do any related rate problems, before you take a derivative, make sure you have all the information you're going to need. If you don't have the rate at which a variable is changing, you got a problem. Get the variable out. Okay, so let's rewrite this. Spend my life looking for my virtual pen. Pi over 3. Okay, I'm going to replace my r with a 1/2 h. So 1/2 h squared and then times h. I just keep calling it h. Can we just agree to call it h? Because I keep calling it h. I'm the worst. I'm sorry. Okay, so if you simplify this equation, which I want to do because I don't want to have to do too much work in my derivative, this 1/2 squares to a 1/4, so I can pull it out here and make this a pi over 12, and then I have an h cubed. So let's take the derivative. Look at this. When I take my derivative, I'm going to have a dv dt, perfect. I'm going to have an dh dt, perfect. I need both of those things involved, right? One of them is given, which is important. One of them is what I'm looking for, and I got nothing else in my way. So now we're home free. Now we can take our derivative. So I have that the dv dt, the change in volume with time, is going to be 3 times pi over 12h squared dh dt. So dv dt is 9. Grab a different color here. This is 9. I have a pi over 4. My height at this moment, I know, that's my 6. And I'm looking for dh dt. That's the big question. I got only one variable. We're good to go. We can solve. All right, so let's see. This is 36 divided by 4 is 9. So we have a 9 equals 9 pi dh dt. So if you divide both sides by 9 pi, you get that dh dt is equal to 1 over pi, which is kind of a neat answer. And we have to make sure we put units on it. So remember, height is in meters, time is in minutes. So this is going to be meters. Oh, I'm sorry, height is not in meters, it's in feet. This is going to be feet per minute. There's our answer. dH dt is in feet per minute. Okay. Now, I know this is a lot. The first time you see a cone problem, it's a lot. Which is why I got you this monkey. But we are going to practice some more tomorrow. And again, we see this problem over and over just in variations. So we will do some practice with conical tanks and other related rates over the next few days. All right? Okay. I'll see you soon. Oh, put any questions in the end. Don't forget.